Good morning, students. Today our topic is abnormal molecular mass. Students, in previous video we have discussed about the colligative properties. We have studied four types of the colligative properties. First one was lowering in vapor pressure. That was the equation for lowering in vapor pressure. Second one was elevation in boiling point. Elevation in boiling point del Tb is equal to Kb into m. And third one was depression in freezing point. And fourth one was pi is equal to CRT, osmotic pressure. So student, in previous class we have discussed about these four equations. These are the equations for the colligative properties, and these equations are used for calculating molecular mass of the solute. Molecular mass of solute. But student, sometimes in some cases when we determine the value of molecular mass by using these equations, so sometimes we do not get expected value. What do we need? We get the molecular mass of the solute different from them, different from the expected value or different from the theoretical value. Why do we get different values? Student, because these equations are followed, they are satisfied only in some situation, in some conditions. So these are the what are the conditions at which we can calculate the molecular mass of the solute by using these equation of the colligative property. So first of all, our solution should be dilute. Solution should be dilute. These equations are followed by dilute solution only. Why is it? Because if we take the concentrated solution, then mass concentration of solute will increase in the solution. And student, this property will depend on the nature of the solute due to presence of the more concentration of solute into the solution. But colligative properties are those properties which depend only on nature, only on number of the solute particles. They do not depend on nature of solute. Nature of solute. But if we take concentrated solution, then amount of the solute will increase in solution. Okay, so they will start to depend on nature of the solute. So we will take diluted solution only. Then these properties, these equation will be followed by the solute, otherwise not. Second one condition is that the solute should not undergo association or dissociation in solute should not undergo association or dissociation. Then these equations will be followed, otherwise not followed. Or we can say these equations are followed only for non-electrolytes. Non-electrolytes. Because non-electrolytes do not undergo associate, they neither associate or nor dissociate into the ions. Okay, so these colligative properties are satisfied only for the diluted solution, and they are followed only for those type of the solute which are not associated or dissociated into the ions. Student, in case of the association, what will happen? For example, if I take acetic acid, this is the formula of acetic acid. If I take 2 molecules of it, then they get associated with each other, they get dimerged and they form one molecule. Why they do get dimerized? You can see, I can write molecule of acetic acid in this way, okay, and second molecule of acetic acid, this one. Student, you can see, here these two molecules form hydrogen bonding. They form hydrogen bonding. They form hydrogen bonds. So due to formation of hydrogen bond, this is more stable. This is more stable. So they undergo dimerge very easily. Okay. So if we take 2 molecules of acetic acid, then they dimerge and form 1 mole. So you can see here we are taking 2 mole, 1 mole of this and second one this. But after association, we get only 1 mole. Okay, so number of moles are changing here, and colligative properties are dependent only on number of the solute particles, and number of moles are changing here. Okay, so we can say that the value of the molecular mass will also change here, because here I can write this equation in this way also. 2 mole of acetic acid, after association they give just this. So here mass of acetic acid, this is 60 gram. You can calculate. Mass of 1 carbon is 12. 3 hydrogen, so mass of 1 hydrogen is 1. There are 3, so total mass of hydrogen is 3. Mass of carbon 12. Mass of 1 oxygen is 16. There are 2 oxygen atoms, so mass is 32, and mass of this hydrogen is 1. So after adding, you can say it will be 60 gram. But student, after association, they give us mass 60 into 2. We will get 120 gram. Okay. So student, this is the theoretical value for acetic acid. But after association, we observe this value. Mass is 120 gram. So students, this is the abnormal mass. Abnormal mass is that which we get after association or after dissociation of the molecules. Okay. You can take one more example. In case of dissociation, for example, if I take NaCl, student, it can dissociate into the ions Na plus Cl negative. Here we have only 1 mole of the sodium chloride, but after dissociation they are giving us 1 mole of Na plus and 1 mole of Cl negative. So we are taking only 1 mole, but after dissociation we are getting 2 mole. So again here number of moles are getting changed. So due to changing in number of the moles, colligative property also change. Students, in 1886 a factor is given by the Van't Hoff, and this is known as Van't Hoff factor. It was given by Van't Hoff in 1886, so it is known as the Van't Hoff factor. Students, this factor express extent of association or dissociation of solute. Dissociation of solute in solution. Means it tells us how much solute is associated or dissociated. This factor is denoted by I. Van't Hoff factor is equal to the normal molar mass divided by the abnormal molar mass. So we can say that Van't Hoff factor is the ratio of normal molar mass to the abnormal molar mass, or I can say normal molar mass or theoretical molar mass, abnormal molar mass or observed molar mass. Student, you know very well, molar mass and colligative property, these are inversely proportional to each other. So we can say Van't Hoff factor is also equal to the ratio of observed colligative property to theoretical colligative property. Value of this Van't Hoff factor is always greater than 1 for dissociation. Because in case of dissociation, molar mass get decreases. Here observed molar mass is less. So total value as compared to normal molar mass. So value of I will be greater than 1 for dissociation. And for association, this value of Van't Hoff factor will be less than 1. And if any solute neither associate and nor dissociate into the ions, then Van't Hoff factor value will be 1. You can see for association. First of all, we will see dissociation. Students, if we take NaCl, 1 mole of NaCl, it dissociate into two ions, Na plus and Cl negative. So it gives us 1 mole of Na plus and 1 mole of the Cl negative. Here I am taking 1 mole only, but I am getting 2 mole. 1 plus 1, 2 mole. So here, what is the Van 't Hoff factor? Van 't Hoff factor is, here observed value is 2 and normal value, theoretical value is 1. So Van 't Hoff factor is 2. Okay, so it is greater than 1 for dissociation. And how can we calculate, how can we derive formula for this? For example, if I take A, let us consider it is dissociated into the Na. If we have maximum concentration of reactant at time 0, so here value of Na will be 0 because at time 0 reaction is not started till now. After time t, let us consider alpha particles get dissociated. Okay, so here n alpha particle will form, because if we are dissociating 1 mole, then it is giving us 1 plus 1, it is giving us 2. So if we are taking n, if we are taking An, so it is giving us A plus A plus A plus A, means N type A. So it will give us alpha plus alpha. In this way it will give us N alpha. So student, from here what will be the value of Van 't Hoff factor? From here, value of Van 't Hoff factor will be the normal value, okay, sorry, it will be the observed. Observed is 1 minus alpha plus N alpha divided by theoretical. Theoretical value is 1 divided by 1. So from here I is equal to 1 minus alpha plus N alpha. I take 1 this side, so I minus 1 is equal to N alpha minus alpha. I can take alpha common here, so take alpha common, N minus 1. So from here alpha is equal to I minus 1 divided by N minus 1. So this is the mathematical expression of the degree of the dissociation. Okay, so with help of the Van 't Hoff factor, we can calculate how much solute is dissociated. Okay, students, for association, how can we calculate? For example, if we are taking Na and after association it is giving us An. So let us consider at time 0, value total concentration 1, for product it is 0. At time t, let us consider that alpha particle get associated. Okay, so after association, for example student, if we are taking 2 moles of the acetic acid, then we are getting only 1 mole after dimerization. Okay, so we are getting only 1. So what will be the value of Van 't Hoff factor? It will be 1 by, what was the total normal value? It was 2. So it will be 0.5. Means Van 't Hoff factor is less than 1 for association. Okay, so here if alpha particles are getting associated with each other, then we will get how many particles? Alpha by n. So now what is the value of Van 't Hoff factor? It is observed value. So now how many moles are there? 1 minus alpha plus alpha by n divided by theoretical value. What was the theoretical value? It was 1. Again calculate this one. So 1 minus alpha plus alpha by n. Take one that side, I minus 1 is equal to alpha by n minus alpha. Take alpha common here. So I minus 1 is equal to, take alpha common, 1 by n minus 1. So from here alpha is I minus 1 divided by 1 by n minus 1. So this is the formula for calculating degree of the association. Means how much solute is associated. Okay students. So students, now we will write the colligative properties. That was the colligative property for lowering in vapor pressure. But if we have electrolyte which is associated or dissociated, then we will write in this way. When to factor into XB, mass of the solution. For elevation in boiling point, we will write in this way. For depression in freezing point and for osmotic pressure, means we can say that colligative properties are directly proportional to the Van 't Hoff factor. If value of Van 't Hoff factor is increases, then colligative properties also increases. Okay, for example, if it is asked to you that which of following have highest value of elevation in boiling point. Boiling point. Okay, let us consider we have options. A, 1 molar NaCl, 1 molar MgCl2 magnesium chloride, 1 molar aluminium chloride and 1 molar urea. So student, first of all we will see here concentration is same. Okay. So we will see the Van 't Hoff factor for that. Here it can dissociate, sodium chloride can dissociate into 2 ions. It can dissociate into the 2 ions, Na plus and Cl negative. So it is giving us 2 ions after dissociation, MgCl2. It will give us Mg2 plus 3. Ions after dissociation. AlCl3. It is giving us Al3 plus 3Cl negative. Okay. So 3 chloride ion plus 1 aluminium ion. Total 4. And it is non-electrolyte. So it is giving us only 1. It is not dissociating. So here number of ions are increasing. Okay. So value of molar mass will get decreases. Okay students. So here Van factor value will be maximum. Because here value of I is maximum. So for this value of elevation in boiling point will be maximum. So this will be the right option for this one. So from here we can say value of colligative property is also dependent on the value of the Van 't Hoff factor, and it is directly proportional to the Van 't Hoff factor. Okay, so I hope it is clear to you. Thank you. Have a nice day.